So this is the second to last lecture. Oh, I know. So we are going to talk about Comp 40 today. Normally I say, look, go away if you don't want to talk, if you don't want to learn about Comp 40, but it's actually kind of interesting stuff, I think. Now I'm not going to, I will hide my eyes if you like walk away, and I'm not going to stress about it. But if you are thinking of taking Comp 40, then I say stick around. If you're not, stick around as well. All right, but it's up to you. If you got other stuff that's more important or whatever. A couple people have asked me about hackathons. I've been meaning to bring this up for a little while. Anybody been to a hackathon in here? A few people? Yeah, are they fun? Yeah, some people are like, it's like tiring. So a hackathon is basically you go to some place and spend like 24 hours coding stuff with teams, and it's fun, and there's pizza, and there's t-shirts. You always get a t-shirt. And you spend 24 hours doing this. Tufts has a couple every year. This one happens to not be a Tufts one, but I've seen a couple posters for this in Halligan, and I thought maybe I'd mention it up. April 25th and 26th is 2 weeks from, or not this weekend, but the next weekend. And this is just a hackathon you can go to. Now, why is Kayak, which is like this travel website, why are they sponsoring it? Because they want to hire you guys, right? So they like companies will sponsor these hackathons so that they can find the talent. And guess what? You guys are the talent. So anyway, if you want, this one happens, I don't know much about what the deal is, but you can go and check it out and see what the thing is. There's prizes, and I don't know what the prizes are. Maybe it's a trip to somewhere. I don't know. I doubt it. But you never know. Kayak might do that. Do you remember what the prizes are? Cash prize. OK, well, you can buy a trip somewhere with a cash prize. Although if it's like 20 bucks, then maybe not. Lots of T tokens, right? OK, so anyway, I thought I'd bring that up. OK, as far as today goes, here is what we're going to talk about. Like I said, it's going to be kind of a prep for Comp 40, although I'm not making it specific to Comp 40. I will talk at various times during the day about what Comp 40, like what parts of Comp 40 are you need to prepare for. But we're also going to talk about some lower level stuff than we've talked about before. OK? So don't let this stuff scare you. I'll scare you a little just because I want you to be ready to take it. But no, do not let it scare you. The dirty secret is, if you do your work in Comp 40, you will do fine, right? Doing your work might mean like 40 hours a week in smelly Halligan or something, but it only gets smelly at like 4 in the morning when people have been there all night. But it might mean that, but you will do fine in the class, and coming out the other end, you'll be kind of happy about it. All right, so here's what we're going to talk about. I got a couple class logistics for last, because we're getting kind of to the end here. And then we're going to talk about Comp 40. It's done in the C language and assembly language, which is slightly different than C++. So we're going to talk about that. We're going to talk about lots of different differences between C++ and C. And then we're going to talk about hexadecimal digits. I happen to have written the hexadecimal digits on the board up here, right? 0 through F, which might seem a little odd, but we'll talk about what that's all about. And then we're going to do binary notation. I've also written the binary numbers up here, 0 and 1, right? There's only 2 of them. So we'll talk about that. All right, any questions before we get going on Boggle or anything else? OK, here's one thing. OK, first things first. So I hate to say this is actually disappointing a little bit. So remember at the beginning of the year I talked about, I hate to start on a downer. Remember at the beginning of the year I talked about how last semester we caught a bunch of people cheating in this class. For what it's worth, I have not caught anybody cheating in our class, so thank you very much. If you're getting away with it, you're just wait. I'm still got to do some tests for at the end of the semester. But I don't think, you are all innocent until proven guilty. And I think you're all innocent, for what it's worth. However, Comp 11 has had some issues. And one of the issues is that people who took Comp 11 before, which means some of you guys, maybe not in here, but the other section, whatever, have been giving code for projects to this year's class, this semester's class. And they're going to crack down on it, right? Which means that you might get an email in the next couple of days saying, we need to talk to you about your Comp 11 stuff. I would suggest preemptively talking to me if that's the case, if you've been giving your code to people, because you need to deal with it. And I don't want you to get in big trouble. I mean, I want you to get in trouble because it's not what you should be doing. But I want you to be come up with it. So just to let you know, we're doing checks, and it is so easy to do these checks. If you've been giving code to other people, we find out about these things, right? Because it's just not hard to do. It's all digital. It's easy to do. Anyway, enough about that. Like I said, I'm not accusing any of you, although I've seen the list of people, but not accusing anybody. OK, enough about that. And I still love you guys. I do. Next week's lab. So this lab was this last Monday's lab. I kind of didn't tell all the TAs to tell you guys this, but it was the last lab, right? So if you want to go thank your TAs or something like that, or other things, but if you want to thank your TAs, you can just email them and say, hey, thanks. I'm sorry, this is the last lab. I didn't say thanks and whatever before. So I apologize about that. Next week's lab, you might get one more chance. Next week's lab, remember how I said, is anybody interested in cryptography and might want to do stuff? I'm going to try to come up with a lab this weekend. Well, I'm going to. It might take me all weekend. I'm going to come up with a lab this weekend that's on some of the cryptographic stuff, like public and private key encryption and some other stuff that I think is kind of interesting. And it'll be a completely optional lab. It'll be if you come if you want. If you don't, no worries. Monday, I'll hold one lab because Monday's a holiday. So I'll hold one lab, and it'll just be me, or maybe the TAs will show up. But I will publish that ahead of time. And then Tuesday, we'll have the regular lab schedule, but completely optional. OK? But I think it'd be kind of fun if you want to delve into this stuff a little bit. And certainly, you can do it on your own as well. But it'll be out there. OK? So that'll be good. Lab grades. I'm going to post all the lab grades this weekend as well. Here's the deal. Because of all the snow days, and because I'm trying to be a little bit nice, which is wholly against my grain. I'm not a nice person. But I will post them all. If you get a 0 for a lab and you haven't done it, go do it. And then submit it. And let me email me and say, just submitted the lab. Please change it. Then we'll count it. OK? So I'm going to give you extra time to do these labs. I want you to do the labs. Instead, I don't want to punish you for missing a day or whatever. Just do the labs, and you'll get credit for them. Does that make sense? OK. That's about labs. And if I screwed up on grading, email me that too, and say, hey, I did do this lab. Why did I get a 0 for it, or whatever? OK. Did you have a question, Camille? If you get a 3 out of 4, can you still redo it? Sure. If you want to still redo it, you can redo it. But now I'll probably have a million redos, but that's all right. I would rather you do it correctly, right? It's also going to be good study for the final if you didn't get it right the first time, right? OK. All right, Boggle, next Wednesday it's due, I believe. It's 22nd, I think. I'm going to be here Monday. So I'll be in my office or in the lab, running around the lab. So if you have questions and you're still not getting stuff, stop by or email me and see where I'm going to be and whatever. I'll go to lunch or something, but otherwise I'll be around. OK? Last lecture's next Wednesday. It's going to be a review. So there's no more new stuff. Right? Today's new stuff, but I'm not going to test you on it. Next week's just going to be a review. Similar to the last review session before the mid-year, it's going to be all stuff we've covered since then and kind of prepping you for types of questions you might want to study. OK? And then let's see, what else? Oh, the other thing about the test. So I know the mid-year was long. I'm going to make the final a little shorter. OK? I promise you it will be shorter, or at least I'll try. OK? I mean, it'll still be a good length test, but I will try not to kill you guys with long questions, like a recursive long poem or something. All right. Next thing, I got an email today to try to remind you guys to do your course reviews. This is a good chance for you to say that provide feedback so that we can make the class better next semester. OK? I'm actually not going to teach data structures next semester. It looks like Professor Sheldon will. I'm going to go to Comp 11. But any feedback you have about what worked well, what didn't work well, this and that, you can put comments about whatever you want in there, basically. Constructive feedback's always appreciated. But try to do that. Technically, I think you're supposed to do that before your final. But because you have extra time, it doesn't actually matter. So if the final's too long and you hate it, then give me a bad grade for it. But try to do it before that if you can. All right, and then finally, the final exam. Last day of class. It's in class right here. We'll knock it out, and then nobody has to worry about reading period and all that. OK? If for some reason you have 7 tests that day, let me know. We'll work something out. All right, any questions about logistics? OK, good. All right, let us move on to a little bit about Comp 40. Now, for those of you not taking Comp 40, you can just go, ha-ha, all these other people have to listen to this. Here's what Comp 40 is all about, right? You can go from 11 to 15 and generally into 40. Here's what Comp 40 is all about, right? Right now, you're still kind of in the introductory programming abilities, right? You're getting better, and Boggle is definitely a test of raising it to the next level. right? You go into Comp 40 and all of a sudden you're like, start at the Boggle level. Like your first project's like at least that hard, right? So it's like, boom, you're right into it from day one. But you are going to become a much, much better programmer, okay? I love the fact that you guys have all become, trust me, if you look at your programs from day one in this class to now, they're so much better now. You guys have all improved, right? But in Comp 40, you'll actually study much more in detail the lower level stuff to the point where you're going to get down to the computer hardware level, talking about how does a cache work and how does virtual memory work and all these kind of really low level, kind of nerdy fun stuff that I actually love because I'm a computer architect, right? And you figure out how all that works together to make your programs faster. Okay, and you do some really fun assignments as well. What's the bottom line in all this? Or the bottom lines, right? You're going to talk about low-level C code. I'll talk on the next page about C itself. And then you're going to go into assembly code. What's assembly code? Any ideas? Yeah?
Is it like one step above binary?
One step above binary code. Yeah, so your computer only knows some things. It only knows at the hardware level how to do some things. The assembly language basically tells the computer, do this one thing. Move memory from this location to this location, 1 byte, right? Jump from this program line to this program line, right? Or add 1 to this number. There are very few number of statements. Assembly language is where that goes. And then the next level is the binary machine code itself. You're going to talk one level above that. So you get really down into the details. And it's hard to write assembly language programs because they're like really long. They end up being really long because you have to tell it to do every single little step. You think writing a for loop's tough. Wait till you try to write loops in like assembly language. It's like, you know, an extra 7 lines. Right? Because it's like you have to tell it, OK, now increment this one, and now do this, and now jump here, and testing. So it's very low level. But it's kind of fun, too, and you really get a better picture for what's underneath your C code or C++ code. The cool thing about 40 is you're always working with a partner. Every assignment, you'll have a partner, right? Which is cool because, and you switch partners. You can have the same on a couple of assignments. But you'll switch partners. You'll meet tons of people. You'll be able to rely on them. It'll also keep you honest. Right? Because you can't like wait till the last minute to do your assignment because then your partner's going to be upset. Now, if you both happen to be procrastinators, well, that happens. But most of the time you feel a little guilty, right? If you're trying to keep, you don't want your partner to fail because you can't get out of bed or whatever, right? You have design documents. You're going to have to design your programs before you submit them. We probably should have done that more this semester, but you can put that in your constructive feedback. And then there's going to be a lot of reading. I'll show you where to go there. And this summer is not a bad idea to go do some of that reading. OK? Why do we teach this class, Comp 40 and C? And what's the difference between C and C++? Well, C was originally designed to be as close to assembly language as possible while it's still being a high-level language. All right? It was designed at this very cool place called AT&T Bell Labs. I think we've talked about them with Unix before. And it was designed primarily for Unix so that if you have two computers that are both running Unix, but maybe different underlying hardware, you can still write one program that will run on both computers, okay? Which is very cool. It's a portability issue. And they did this, right? But they made it pretty close to metal, which means that, well, actually, I think it's, there we go. This is one I wanted to show you. Going from C++ to C. C has the speed and efficiency of assembly language combined with the readability of assembly language. Assembly language is not that easy to read. C is not that easy to read, but you guys are actually C++ programmers, so you're getting there. OK? You're getting there. Now, what's the big deal with C itself? Well, it happens to be a really popular language. Last year when I showed this, actually, C was number 1. It actually slipped down 1 this year. Here's what happens. There's a site that does this. It's called the TIOBE index. They measure basically how popular computer languages are. OK? Notice the first top one's actually Java right now. It kind of swaps with C every so often. C is also way up there. C++ is also way up there. So that's kind of why we're teaching UCI C++. Anybody know what Objective-C is for? iOS, the iPhone, right? It turns out that Objective-C, up until a few years ago, was never heard of. Right? Well, not really never heard of, but nobody used it. And then all of a sudden the iPhone came out, and then whoop, it's all of a sudden popular. Some other languages, JavaScript's a big popular one. Python is pretty popular. I'm not sure why Visual Basic's so popular anymore, but I guess it is. But there's lots of different languages, so it's really popular. Showing this in graph form, they actually show this too. This is actually kind of neat. The black line there is C. It's always been one of the top most popular programming languages, right? It's always been really popular. And the other ones have kind of gone up and down. Java, my pointer's not working again. Java is Java's pretty popular, was really popular in the early 2000s, and then kind of dipped down a little bit. It seems to have jumped up a little bit now, but many other languages are coming in that are doing that. The orange line at the bottom is Objective-C, and if you'll see, it's 0 all the way up, and then all of a sudden the iPhone came out right here, and it went right, and then right here, this other language called Swift came out, which is the other language you can program iPhones with. And so Objective-C is like, ooh, because Swift is now getting more important. And it's probably a better language anyway. So as it turns out, you can, that's that. But anyway, bottom line is C is really popular. And that's one of the reasons we teach assembly language in C, or Comp 40 in C. And not only that, it's really close to assembly language, which means you can do lots of stuff fast with it. It's not fast to program it, though. But you can, the programs run fast. OK, this is the most important thing you're going to see today. This is the reference material for Comp 40. The page is here. I clicked on it earlier, so it still exists. It was there last semester, too. The page says a bunch of reference material, 40 readings, course coding standards, blah, blah, blah. Read those before you get to class. Don't wait till class starts to go read these things. They're kind of long documents, and it's important to get to know this stuff, right? And it's kind of, it's good reading. And what else are you going to do this summer? Go outside? Come on. All right? You're not going to do that, right? Coding standards. I was pretty lax about our coding standards. Remember I gave you that document on commenting guidelines and whatever? We really weren't that specific about it. In this class, you have to be really you have to follow a format for your code pretty distinctly. So you have to do that. So make sure you read this stuff. Go to the reference page, troll this. It'll at least be up for the next couple weeks. And I don't think it's going to be taken down before the semester begins. It might be changed a little bit. But that's that. OK? All right. So as I said, C is kind of not the most easy to learn, easy to read language, although it's very similar to C++ in that it has the same for loops, it has the same while loops, it has the same, many of the same variable types and all that. These are the things that are the same. Okay? Built-in data types. It's got ints and chars and floats and doubles and long and unsigned integers and all that. Same. Exactly the same. Array indexing is the same. You can say array bracket 4, and that gives you the 4th element in your array. Okay? Well, actually, I guess the 5th element in your array. Function declarations, exactly the same. Modularity, you're going to have to use .h files. One of the professors who taught it in the last couple of years said, did you tell your students they could make main.h files? And I said, I didn't tell them that. Somebody made a main.h file. There is no main.h file. You can do it, but it's not normally used. Main is the C. You don't really generally have a .h file for main. You include other things. So it'll embarrass me if you do that. But all the other things, the flow is the same as well. So all this stuff will be very familiar. The things that won't be familiar, there are no strings in C. And you go, well, why would you do that? Right? Well, strings are just null-terminated arrays of characters. Hello, H-E-L-L-O 0. And the 0 is the null character. Okay, it's not an actual 0. It's like the digit 0, not the character 0. That's what strings are. Okay, you get to manipulate those at the array level. Why is that the case? Because that's the way assembly language does it. You've got a piece of memory, and your characters are there, and that's your string. Okay, that's how it works. There are no classes. The whole point of C++ was introduce classes into this whole thing. There are no classes, no objects, no constructors, no destructors. And you'll go, yay. Well, you got to still do your memory management. It's actually lower level. All right? So you have to do that. Memory management, you use this thing called malloc, which says memory allocation, which is exactly like new, except entirely different. Okay? You do the same exact thing. It does the same thing, except you have to know more about what you're trying to ask for. I'll show you an example in a minute. You have to actually provide the size to it of how many bytes you want, how many actual things you want to put in there. You have to give it not only just things, how many bytes of information you have to do it. To free memory, you use free instead of delete. That really is pretty much the same. Right? If you have a pointer that you're freeing, if you asked for it, you free it. That's the idea. Okay? There are no passing by references. We didn't talk too much about that in here, but you just can't do it. You can pass by pointers. Everything you can do is, everything you pass is by pointers. Pointer, pointer, pointer. Okay? That's something else we probably should have talked a little bit more about in this class. But remember, part of this class was understanding the data structures, not really the lower level stuff. But you'll pick it up pretty quickly. No Boolean. Doesn't exist. You get either a 0 or everything else. Everything else is true. 0 is false. That's the way C works. Okay, so if it's 0, it's false. Everything else true. Negative 20, true. 14, true. Okay, that's the way it works. All right, questions on those? We're going to go through details in a minute. Okay. What do I mean when I say strings are null terminated? Well, I kind of mentioned it earlier, but there is no string class. There is no string class. You can't use strings, and there's no cout either. Okay, we'll talk about what you do instead. Strings are just the characters. The final character is this null character, which we've used nulls for linked lists and things, and trees. You have to, anybody ever heard of a buffer overflow? A couple people have, yeah. Buffer overflows are the way hackers steal your passwords. Okay, here's how it works. If you declare a string, you call it a string, whatever you want, you call it a string, it's just an array. If you say that it's 256 characters and you try to put 257 things in it, in fact, if you try to put 256 things in it, it'll also possibly crash. But if you try to put 257 things in it in particular, you go past the amount of space available to you, and the compiler goes, you know what you're doing, right? So I'm not going to bother you about it. Well, you have to, if you don't know what you're doing, and you let this happen, then people can access memory that you don't actually have control over, and therefore they can maybe stick some other programs in there, change your stack, make it so that their program runs instead of your program running, and there goes your password. It's a little more subtle than that, but that's the way it goes, right? So it turns out you can use, there are various ways of inputting strings. If you say, if you get a string that's 256 characters long, it will actually, I believe it will only let you do 255 because the last character is defined or should be that null character. Okay, but you have to be careful about it, right? You just have to be really careful about how it all works. Okay, a little different than strings where you just, the string keeps expanding if you keep making it bigger. Character arrays do not. Lower level, much lower level. Okay? Whoa, what can we do with strings? Well, with C strings, there are a bunch of library functions to do things with. You can compare strings. Comparing's a little weird. When you compare two strings, one can either be bigger, or rather alphabetically bigger, greater, or alphabetically less, or equal. And if they're equal, you get a different answer. If string 1 is less than string 2, you end up getting a negative return value. Anything negative, it's just negative, right? 0 if they're the same, and positive if it's greater. So it's kind of a ternary, like 3-state response. Okay? You can do that. There's also concatenation. Notice these are all pointer things, by the way. You're always passing around pointers to these things. There is a copy function. You should almost never use this copy function. You should use another function which actually limits the size of the copy. Because if you do this, if you do a copy and you don't have that terminating null, or if you don't have enough space, it will copy right over into extra space you don't own, and your program will crash, or somebody will steal your password. It's more subtle than that. But that's that. Okay, so there's lots of, you can also find a string length and so forth. So there's functions you can do. They're just not as robust or as easy to, they're easier to mess up than C++. Okay? All right, what else? Well, structs. We use structs in C++, but remember, structs are almost exactly like classes. Structs exist in C, but they're not classes. They're similar, but they're not. You still define a struct, right, with a, you call it a struct, and then you put something in it, just like we do in C++. But then, if you ever want to declare a struct, you have to say struct, your name of your struct, and then the name of the variable. I wish the pointer was working right here. So you say the name of the variable there. Okay, so it's a little bit different. And by the way, you don't have to memorize this now. Just go back to this if you ever need to figure it out for Comp 40. You can also use this thing called a type def, which is part of what I've done in Boggle for you. So you can see how that's used. But that basically says, call my struct name, and then I can use it later. Or struct name t in this case. Okay, so you'll see how it works when you get to it. But just know that structs are a bit different. They still hold all your data for you. Unlike kind of like a class, except you can't have functions in them. Okay. So let's see, what else? Things that all those things you might have heard about before. There's this weird thing called a void pointer. A void pointer says, you know how you can have a pointer and it's an int pointer? And you can say int asterisk a. And that is a pointer to an integer, right? You can also have a void pointer a, which is a pointer to we don't know yet, right? That's what that's all about. You actually don't know what it's a pointer to. And the reason we do that is because you could end up making it point to pretty much anything, right? And the way the language works is it says if you don't know what it is, you can call it a void pointer for now, and it will allow you to later cast it to something else. Okay, casting, we've talked about that before. If you say, let's say you had int a and float b, and you said a equals 2 and b equals a. Well, actually, this is not the best example. It would be better if you did the other way. If you said b equals 2.3, and then a gets b. What is a after you do this? Anybody know? It's 2, actually, because it turns the b, which is a floating point value, into an integer, because a is only an integer, turns it into an integer, and it hopefully warns you and says, hey, are you sure you want to turn that float into an integer? Because all it does is it truncates it. It just says what's left. It doesn't round it or anything. It just truncates it, right? So normally you'll get an error warning here. It won't be an error, but it'll be a warning. So what you can do instead is you can say, I know what I'm talking about. You can say a, and then you say int b, like that. And that will say, don't warn me. I know that I'm converting that b, that floating point value, into an integer. I know. And there's reasons you might do that. Okay, but you would have to do that if you want to avoid the warnings. Okay. We've talked a little bit about pointer arithmetic. We're going to do a little example in a minute about pointer arithmetic. But pointer arithmetic is used instead of bracket notation a lot of times. Instead of doing the bracket, you'll use pointer arithmetic. Why? Sometimes the math seems to work out a little more intuitively. You'll see in a minute. Well, the example I give today is probably not the best one, but you'll see. Now, we also, remember, you know how we use the // for comments? In C++, they kind of are in Comp 40, they kind of require you to use the slash asterisk and asterisk slash ones, which are kind of painful because you can't nest them. It's too bad. But that's part of this coding standard. It used to be that you could only ever use those, but now you can use the other one, but not in class. OK, pointers. Or I guess void stuff, but first. We talked about malloc and free. Malloc and free and size of are how you're going to deal with memory. Okay, you can't use new and you can't use delete. So what do you do instead? Malloc is what you do to reserve the memory. This is from the heap, which is the part that's kind of the large part of memory that you ask for space from the operating system, right? You pass it the size in bytes. And a byte is 8 bits, which is basically a small number, right? 0 to 255. That's what you get to. You ask for how many of those do you want. Okay, we'll talk more about that in a minute. Size of something gives you the size of that. So size of integer, if you say size of int, returns the size of an integer. Turns out on our computers, generally that returns 32. Right? Or rather 4 bytes. It generally returns 4, which is a 32-bit integer. What does that mean? Well, it means that an integer has the ability to store numbers as big as 2 to the 32. Remember how big that was? We mentioned it once in class. Close, 4 billion. A little over 4 billion. 2 to the 32. Okay? That's how much an integer will hold. And if you do size of int, it will tell you that. So if you want to request 10 integers from memory, you have to know that you're going to get 40 bytes worth, because 4 times 10 is 40. And you can do that by doing 10 integers times the size of an int. And this is a portability thing. Some computers have a different size for int. Why? Well, not necessarily the best decision, but that's the way they used to do it. OK? All right. Here's how you actually do this. Turns out that malloc returns a pointer. But malloc can return a pointer to anything. This is where the void pointer thing comes into play. Okay? You can get you ask for something with malloc, and it returns a little void pointer which says, whatever you cast this to, it'll be fine. Right? It'll work out. So here's how you get 10 integers. You declare an integer pointer, and then you set the integer pointer equal to, cast it to an integer pointer, because that's what you're getting, and then you do malloc and the size of that integer times however many you want. Right? And that's how it actually works. This will give you 4. 4 times 10 is 40. You will get enough space to hold 10 integers. Okay? So this is kind of how it goes. All right? If you run out of memory, you get null back from the system. If that happens, you're probably in trouble. In general. Lots of things will start crashing. But it doesn't happen that often anymore. Questions so far? I know I'm flying through some of this stuff, but it's, yeah. Malloc store for, I think, memory allocation. Basically allows you to get memory from the system. It's like new, except you have to supply the bytes. Okay? Free is much like delete. If you've already done new, or if you've already done malloc, rather, and you free that pointer, it will go, here's the memory back. And you can't use it anymore. It's just the same rules as delete. None of this bracket business like with delete. Okay? You have to do that. All right. Let's go through a little bit of code here and see. Same idea with the main function. That should look familiar. We have an array of 10 integers here. And then we're going to ask for the 10 integers, the space for 10 integers. And then we're going to do this weird business here. Right? I want you to figure out what's going to go into that array. So do that with your neighbor right now. Take a look at this. Go through this and figure out what is going to go into that array. Let me remind you. Asterisk and then this number means get the address of the next value, or the address of this, and set what's there to whatever this is. Okay? Do that right now. I'm going to write up the array and we'll put it in there. Okay? Figure that out. Okay, does anybody know? What's going to go in that array? Yeah. 0. Why does 0 go in there? When we're at I equals 0, it's going to be dereference what's at int pointer plus 0, which is what the first one, which is the first place in our array. Very good. And it's going to put I times 10, which is 0. And then you said it's going to be 10, and then 20, and then 30, and then 40, and then 50, 60, 70, 80, 90. That's what ends up in there. Okay? Hopefully you guys figured that out. But that's how you would fill in an array, declare it, fill it in, and whatever. The next line's a little wacky, or the next little one. This one is a for loop from 0 to 5, and then this weird thing called printf, and then this weird garbage here. Right? Not garbage, this weird stuff. Okay? And then some pointer math here too. We have to talk about what printf is, because there is no cout anymore. Okay? C++ has cout, C does not. Let's go into printf land for a minute. Printf is how you print a standard out, right? And it writes this formatted string to the output. And the formatted string tells you how to manipulate whatever you want to print out to say how in whatever form you want. Okay? So the format specifiers start with a %, and they tell you what to do with the next thing in this little list you give it at the end. So here's how it works. If I is 22, and you say printf, this is I colon %d, standing for percent like integer. I don't know why it's d, but that's what it is. And then the backslash n, there's no end L. Get used to that too. And then comma I, it says replace whatever the %d is with whatever this is in integer format. And so it prints out this is I colon 22. Okay, %d prints out the integer, 22. If you had said %f, it would have printed out a floating point value. If you'd said %s, it would have gone, I don't know what you're talking about because that's a string. Right? %c would have printed out whatever the equivalent character is for 22, and I don't even think that's a printable character. So it probably wouldn't print anything. But it doesn't ask you, it doesn't say, are you sure you mean this? Clang might actually, but it generally doesn't. Okay? Well, here's all the different things you can do. You've got all these different formats in here. You've got octal numbers. Don't worry about that. You probably won't use that too much. You've got hexadecimal. We'll talk about that later. Floating points, uppercase floating points. I guess it puts the F on it or something. You can put characters, strings. By the way, these are C strings. S is a C string. It better have a null at the end or you'll get garbage printing out. Okay? You can print the address with P, the pointer address for something. Right? You can, I don't know why you'd use N, but sometimes that maybe you would. If you wanted to print a percent, you print %%. And it says, oh, OK, I know you want to print a percent. Right? Lots of different things. Let me show you some examples of that. Here's some examples. By the way, this is on the website too. If you want to know, it's like you can download the code for this. Printf, characters, %c. If you print character A and then 65, that happens to be both A's. Okay? Lowercase and an uppercase. Okay? Lowercase is just the A. 65 is the decimal representation, the ASCII representation for uppercase A. You'll notice I put that in Boggle try if you want to check it out. Okay? Decimals, well, you can print like a regular decimal like 1977 and then a long decimal, like a 64-bit decimal, or I'm not decimal, integer. 64, that should probably say integers actually, not decimals. And it's going to print out like this, 1977 and the whole number there. Okay? If this was a nice long number, it would print all of it. You can do blanks. There's all sorts of things in here. You can do blanks, which will print like how many 10 blanks before the number, right? %10 the number. You can do it with zeros. This is how you do it. It does 000001977, right? Radices, and if you have different radixes, kind of like radix sort, right? We dealt with radixes. This is in different bases. If you want to print it in decimal base or that's hexadecimal or octal, or if you want to put the little 0x in front of it, et cetera, it'll do that. Okay, so there's lots of different ways of printing things like that. Floating point values. I always have to look this up exactly how you want to do this. But if you want to print out some floating point values, there's lots of different formats for that. Right there. Lots of different ways you can do this. Go look at it when you get the chance. You can also do it in exponential notation and so forth. Okay? There's a little width trick. You can print out things with like how long you want the whole. Like if you want the whole thing to be 10 or 5 digits long, you print it out like that. A little weird. You can also, of course, print strings out. Okay? And a string is just a character array. It knows, by the way, that this ends with a little null. So this string is actually one longer than it seems. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's actually 9 long because it's got to put an extra place for that other character. Okay? Lots of different ways to do printf. Okay? All right, so now that we've done that, what is this going to print out? Figure that out. What's it going to print out?
Like you'll skip each one, so like 0, 20, 40.
Why is it going to do 0, 20? We're going from 0 to 5, and we're only going up by 1.
Multiplying it by 2, so like it goes double the distance in the array.
Yeah, so the first one is when I equals 0, it's going to print out whatever the value is at int pointer plus I times 2. So 0 times 2, it's going to print out the 0th one, which is 0. Then it's going to go through again, and it's going to be for 1. It's going to print out the integer pointer plus 1 times 2, which is 2. So that's 0, 1. It's going to print out 20. Then it's going to print out 40, then 60, then 80. Okay, so that's what's actually going to get printed out. And you have to kind of be used to reading this stuff when you get there. Okay, so it's kind of neat in that sense. All right, you will get used to this. Yeah, question, Jim.
Does the compiler know what
Ah, that's a very good point. And this is actually pretty low level. We'll actually get to something similar on the next page, the next thing. But yeah, the computer knows that an integer is 4 bytes long. So when you add 1 to the pointer location, it says, I'm really adding 4. And it goes here. Right? And if you add 2, it's going to say, I'm really adding 8. And it's going to go here. So it knows by the definition of, hey, I know what an integer is, how big it is, because I can calculate it. The compiler can calculate it. Yeah?
You're just never doing it with the void pointer.
You can't do it with a void pointer. There's just no, there's no size associated with a void pointer. The compiler would probably complain at you and go, I don't know, you got to make it a real pointer before I'll do anything with it. Yeah. OK, good question, though. Good question. OK? Yep, add I times 2 times 4 to the address, and that's kind of what we just talked about. Okay, it knows the type because it can figure it out. When you get to programming languages class, you will talk about how the computer knows what types things are and how it determines what types are. It's kind of complicated, but it's kind of neat how it works as well. OK, compiler will figure it out. Including structs, the compiler can tell you how big a struct is. That's kind of neat, right? It tells you that too. So it'll figure it out. It's just math. If you could figure it out, the computer can figure it out. Now, let's get into some more low-level stuff. Right? You're going to do a lot of this in Comp 40. I'm going to show you some right now. If we look at the memory for the int pointer, this is what it looks like on the screen. Okay, you can actually pull it up in the computer if you're using a good debugger or something. You can get this form. And it will show you what the memory looks like. This looks like a lot of garbage. Right? It looks like a lot of nonsense. Okay? Well, we'd better figure out what some of these are. Hexadecimal numbers are in here. Right? And all this business with hexadecimal numbers. Let's figure that out. Let's take a little detour into hex land. I wrote the hexadecimal digits up here. Hexadecimal is base 16. Okay, we're used to dealing with base 10. We can also deal with base 2. Base 16 is another big one we use. Base 8 is another big one. Somebody told me in 3rd grade they learned base 5. I think that's ridiculous. Base 5 is a silly base. Base 12 would be better. Do you guys know why we use base 10? Because we have 10 fingers. Right. This is when whoever was deciding how to count, decided how to count, they went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That'll do. Right? Now you've got 10, base 10. 10 is not necessarily a very good base either. It's too bad we don't have 16 fingers. Would have been better. We would have looked weird, but we wouldn't have known the difference. Right? I don't know. Grabbing stuff might have been harder. I don't know. Or maybe easier. Who knows? But, yeah. Too bad octopus can't count. Base 8's a pretty good one, too. Oh, well, maybe they can count. I don't know. All right, so let's go into hex zone here a little bit. So hexadecimal notation is just using base 16 notation. The reason we have to use A, B, C, D, E, F is because there's 16 digits instead of just 10. And so you need to represent them somehow. And somebody said, well, make them the letters, because we already have those characters. Right? When we look at this memory here, this is the address where our stuff is located. It's going to change from one run of the program to the next. But that's going to be where our stuff's located. And this is all the data. Okay, and this is the next one. And what this is just a hexadecimal representation of that memory location. Here's how hex works. Okay, your computer is basically has a bunch of memory in it, and the lowest amount of memory you can address is 1 byte's worth. And a byte is 8 bits, right? And what it is each hexadecimal digit is 4 bits, because 2 to the 4th is 16. So it's 4 bits long. And each one of these little 2-bit characters is a byte. So this is 1 byte, another byte, another byte, another byte. What does that mean for you? It means that you can figure out what that address is, what that address is, what that address is. You can't figure out any address in between. There is no knowledge of addressing in between bytes. You get a byte. That's all you get. Okay, when you try to address these things. But what's nice about hexadecimal is because that's the case, 2 digits in hexadecimal give you a full byte. So it's nice and compact. Right? The byte goes up to 256, by the way, 0 to 255. You can represent 0 to 255 with 2 hexadecimal digits. How do we do these conversions? right? Well, you've got the hexadecimal digits here. It's pretty easy to convert to hexadecimal. You just have to be able to divide and find remainders, right? Divide by 16. That's how many digits we're in now. The remainder is the least significant digit. I'll show you an example in a minute. In other words, the one that comes to the most right in your number. And then the next one, when you do the remainder, is the next one, and so on. OK, I'll show you how this works. OK? Let's convert 2913 into hexadecimal. 2913 into hexadecimal. 2913 divided by 16. You get 182, and the remainder is 1. That means that the last digit in your hexadecimal number is a 1. Then whatever the 182, you divide that by 16. 182 divided by 16 gives you 11 with 6 remainder. 6 is the next hexadecimal digit. 11 divided by 16 doesn't go in even. It doesn't go in at all, so the remainder is 11. And 11 is the next higher digit. But remember, we have digits that go all the way up to 16. So the 11 is just B. So converting 2913 into hexadecimal, you get B61. OK, that's how it works. Just divide by 16, figure out the remainder. Divide by 16, figure out the remainder. OK, that's how it works. Pretty straightforward. You just have to remember how to do it. And I'm showing you how, so you look it up if you forget. Same thing here. This is just another exact example. Divide by 16, you get a remainder of 13, D. Remainder of 12, C. Remainder of 11, B. Remainder of 10, A. And you have 0 left over, so now your answer is A, B, C, D, because the least significant, next significant, next significant, next significant. OK? Kind of interesting when it comes out, but that's what it looks like. And that's how you do these conversions. Going backwards is the exact opposite kind of idea. You have to, it's just like if I told you 147 in decimal, you said, OK, that's 7 times 10 to the 0 plus 4 times 10 to the 1 plus 1 times 10 to the 2. Exactly the same thing, except now we're using 10 to the 10, or we're using 16 powers of 16. So to do A, B, C, D to decimal, D times 16 to the 0 is 13 times 1. Gives you 13. You add that to C times 16 to the 1, which is 12 times 16, which is 192. Add that to B times 16 squared, and you add that to A times 16 cubed, and now you've converted A, B, C, D into decimal. And if you add all those up, you get 43981 again, and you've gone backwards. OK? Just base conversions. Not that hard, just a little bit of memory. OK? Of how you do it, remembering how to do it. So that's how you go back and forth. You will do some of that in Comp 40. OK? Other questions on that? All right. Let's go back here. The question earlier about how does the computer know these things? Guess what? 1, 2, 3, 4 bytes. We said that integers were how big? How many bits? 32. 2 to the 32, which is equivalent to 4 8-bit digits, right? So you have 4 8-bit digits, right? And guess what? There is one integer. 0, 0, 0, 0 is one integer. And by the way, this is what we were calculating earlier. We were putting this into the array. This is what we were calculating earlier, right? And that is 1 byte, or that is one integer. 1 byte, another byte, another byte, another byte. OK, what did we put in our array? This is, by the way, this is what's represented up here. We put in a 0. Then we put in a 10. 10 happens to be A. Take a look at this up here. There's your A. OK? If this is a one integer and then this is the other integer, the A is right there. But that seems a little bit weird. If you were to write down a number, let's say you were to write down a number using 5 digits, but the number 17 using 5 digits, you would write 0, 0, 0, 1, 7, right? If you were writing a hexadecimal number with 5 digits, or 4 digits, let's say, you would write down, let's say it was, oh, I don't know, 10, 0, 0, 0, A. How is it represented up here? If that's the first digit, A, 0, 0, 0, it's backwards. Backwards. By By the way, this is the part we were talking about earlier. When it increments by 1, it goes from here, and then this one's next, and then this one's next, and then this one's next. But it's a little bit weird that it's backwards like that. Right? There's the next one. Next one, etc. What number are we currently looking at? 14,000. This is the third one in our array. That was the first one. That's the second one. This is the third one. What is it? It's a 20. 14,000 is not 20. Guess what 20 is? 0, 0, 0, 14. If these, I guess these are zeros, extra zeros in there if you want to do the individual bytes. 0, 0, 0, 14. But it's backwards. Here's what happens. When you design a computer, you get to determine how you store your numbers in memory. This is called a little-endian order, as opposed to a big-endian order. And it's actually kind of a cute little title, a little name. Little-endian means that the little end of the number is the lowest one in memory. Memory is going up here. This is location 100203A10. And then it goes up here, and then this is the next line, and this is the next line, and this is like one big long string of numbers. Little-endian says the little end of your number goes first in memory, meaning that we represent 00000014 as 00000014. The bytes are the endian we're talking about. They don't flip the whole number around like you might think. Each byte is in this format. The good news is that everybody standardizes on little-endian, which is not true. Nobody does. We've also got big-endian. The internet is big-endian. If you transfer data across the internet, the first number you get when somebody sends you a digit, if you're sending an integer, is the 0. Then you get the 0, then you get the 0, then you get the 14. It's exactly the opposite, which is kind of a pain because you've got to remember that. Otherwise, your numbers get completely jumbled up. Instead of having 20, you've got some giant number. Right? So you have to figure that out. You will do whole lectures on this when you get to Comp 40, I'm sure. But the little-endian part is still kind of interesting. Okay? The idea is we have not only put one int here, one int here, one int here. We've actually flipped it so the integer is represented with the bytes in the wrong order. Well, an order. Call it the wrong order or not, but it's another order. Okay? Backwards. Oh, crazy. Okay? Questions on that? Let that sink in for a minute, too, how this works. Which number is this 32 going to be? 0, 10, 20, 30, 40, 50. That's going to be 50. Right? And how do you know it's 50? Well, you write it the correct way, 0, 0, 0, 0, 0, 0, 32. And then you divide by 16 and get the remainder. And you end up getting a 5. And then you divide by 16 again, you get 0. So it's going to be 50. Okay? Actually, I lied. It's going to be the other way around. You're going to divide by 16, get 0 remainder. Then you're going to divide by 16 again and get 5 remainder. Okay? So little byte first. Or little part first. Yes?
Why does it give you like the three digits or integers after the last one is coming after the first 10? Or on the very bottom line, it gives you this.
Oh, this is just how the memory is laid out. I only asked for 10, but this is showing me the whole memory. The rest of it could be dead squirrels. It's all dead squirrels. Yep. Good question. Good question. All right. So I don't mean to be scaring you with this. And it is a lot to see in one long lecture, but you're going to have to deal with these kind of low-level stuff. And hopefully some of you are getting excited about it. Like, wow, this is cool. Some of you are going, why would they do this little-endian business? Computer engineers, crazy bunch. OK, so yeah, so here we're looking at 0.00000014, and then converting that to decimal, you get 20, right? And that's the third one over, which was the 20 there. Okay, that's how it works. So it's kind of neat how it ends up coming out in the end. All right. Look at some other ones here. If I change the program and say that asterisk int pointer plus 8, get 0xbeef. So funny story. There's a number of words you can spell with hexadecimal numbers. Beef is one of them. Deadbeef happens to be another one. Right? Did I put? No, I didn't put deadbeef in there. Microsoft is famous for, in their code, they will sometimes, if they want to fill in an area that should be initialized, they'll actually initialize it with 0xdeadbeef, one after another, after another, after another, after another. And that's so that when somebody's debugging it, they can look at it and go, I see all these dead beefs, so that means the memory's been initialized. If it was some other numbers, they go, wait a minute, this should be dead beef. And they do it. It's easier for humans to see that than, I guess, zeros. I don't know. But they come, it sticks out pretty quickly. So it's kind of interesting that they do that. So if we put beef at location int pointer plus 8, let's see where that goes. 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 0, beef. That's how it's represented. Because the little endian byte, which is the EF, is represented lowest in memory. Then the next one, which is BE. Then the other zeros, because we only had, in this case, a 16-bit number. OK, yeah? It's actually one long array, yes. It's put on the screen like this so you can read it, but it's actually just one long array. Yep. And this is the memory locations, right? If you add 4 plus 4 plus 4 to this, if you add 12 to this, you get this. Right? So that's how it actually comes out. All right? No, I lied. If you add 4 to that, yeah, 1, 2, 3, 4, that would come out. OK? So let's see. OK, so we've got that. If we do A, B, C, D, E, F, 0, 1 in location 9, A, B, C, D, E, F, 0, 1. OK? This is how the little endian stuff works. It's a little weird, but it works that way. That's what's in memory. And by the way, when you ask for it from memory, it gives it to you in a regular integer. And it knows how to deal with these things. It doesn't like flip them. It knows because we program it to know that. Right? But that's how it's actually represented in memory. So when you look at memory, you end up with this. OK? Gets weird. That's hexadecimal. We also, of course, use binary a lot. You guys will do a couple big projects where you're doing a lot of binary stuff. You're compressing binary things, and you're looking at binary digits. And you got to do a lot of that. You have to be able to do bitwise calculations. What I mean by bitwise calculations is something like this. If you have two numbers, let's say you have a number 0, 1, 0, 1. Did anybody take an ES4 in here? How about anybody going to take ES4? A couple people will, right. You'll do a lot of this stuff in here. But if we do 0, 1, 0, 1 and 1, 1, 1, 0, and you take each individual bit and let's say and them together, which means if they're the same, it gets a 1. If they're different, it gets a 0. This will be a 0. This will be a 1. This will be a 0. That will be a 0. Because you're ANDing these two numbers together. And you do that what we call bitwise. This bit, this bit, this bit, this bit. And you AND them together. If we did OR, it would be another one. OR would be if they're different, or if there is at least 1, 1. 1, 1, 1, 1. And you do that. Those are the kinds of things you're going to need to know like the back of your hand. OK? And you'll learn all about that stuff. But you need to know those things. Logic kind of ideas. OK? How do you convert binary or decimal to binary? Same thing, except now our base is 2 instead of 16. Divide by 2, get the remainder. And by the way, if you divide by 2, what are the only possibilities for remainders? 0 and 1. This is why it comes out decimal. We win, right? 23 divided by 2 gives you 11 remainder 1. So 1 is the least significant digit. 11 divided by 2 is 5 remainder 1. Etc., etc. 5 divided by 2, 2 remainder 1, 2 divided by 2, 1 remainder 0, 0 remainder 1, or 1 divided by 2 is 0 remainder 1, and you end up with 1, 0, 1, 1, 1. Notice how much bigger in length this number is than this number. It's horrible. Binary digits are not fun to deal with because they get long really fast. Right? What do you do about that? Well, oh, by the way, you can go backwards, of course. Same exact thing. Right? 1, 0, 1, 1, 1 converted to binary, or converted back to decimal, is 1 times 2 to the 4th, plus 0 times 2 to the 3rd, plus 2 times 2 squared, plus 1 times 2 to the 1st, plus 1 times 2 to the 0th. Add them all up, you get back your 23. It's just a reverse process. Okay? but binary is really long. 5 million in binary is this giant number, right? You do not want to deal with those numbers very often. Okay, it is not fun to calculate with those. So what do? Turns out you can very easily convert this binary number into hexadecimal. Remember, hexadecimal is base 16. Binary is base 2. 16 is a power of 2. So you can actually say 2 to the 4th is 16. So it turns out that 4 bits get represented by 1 hexadecimal digit. So what do? If you want to represent a hexadecimal digit 0, it's 0, 0, 0, 0. 1 is 0, 0, 0, 1. All the way up to f, which is 1, 1, 1, 1. Those are all 16 combinations of the numbers 0 to 16 in binary. Right? And so how do you convert this? You go 0, 1, 0, 0. 0, 1, 0, 0 is a 4. 4. 1, 1, 0, 0 is a C. C. This whole big number that was this giant long number becomes 4C, 4B, 40, which is still hard to read, but much shorter. Right? And once you get this in your brain, you'll go, OK, I get it. Not so bad. Okay? Hexadecimal and binary are the two things you're going to use like all the time in Comp 40. Okay? And any other time you go low level. Yeah? Why are bitwise computations important? Well, sometimes you want to mask things. Like you want to say, get rid of part of the number by anding it with a number that has a bunch of zeros in it. So you want to, there's lots of different ways to do that. Whenever you do arithmetic in binary, you have to know how to do these bitwise operations. Whenever you do encryption, you use bitwise stuff. Whenever you do other kinds of baseline arithmetic, you're going to always end up with that with binary bitwise operations. Yeah. OK, that was a lot of stuff. A lot of stuff. Any questions on that? Yes, Jenny. Oh yeah, at the end of this one, what do you think it is? Stands for binary. Yeah, if you write out a binary, like this could be a regular old number, right? Just happens to have 1s and 0s in it. If we put a B after it, it says, oh, that's a binary number. That's how you recognize it as a binary number. We will sometimes put 0x in front of a number to be hexadecimal. 0x AB0C or something. That's a hexadecimal number because it says 0x in front of it. That's how it is. Whew. All right, anything else? All right, that was your introduction to Comp 40. There's references up there. I'm going to let you go early today because it's nice out. And I finished. I'll see you guys next Wednesday or on Monday in lab or Tuesday in lab.